Assalamualaikum and hi everyone, we are from Group 1 and today we are presenting to you about our group assignment project for MAT097, so stay tuned. But before that, let's get to know our group members. Me as a team leader, which is Anik Razif bin Amirul, and then we have Ain Iman, Aizat Imran, Alia Umaira, Ainul Maria, and the last one is Nur Idila Darwisha. For the task 1, this task is mainly focused on the application of first order differential equation to the total population in Canada from the year 2003 to the 2023. The implementation of the MAT097 model used in the task 1 is to find the gross population in Canada. So, the MAT097 model assumes that the rate at which the total population in Canada increases at a given time is proportional to the number of populations at that time.
Hi guys, have you guys ever thought on how big the human population in this country? Let me show you guys a table referring to the population growth in Canada. So here's the table on the population growth of Canada. For this assignment, we choose the year of 2003 until 2023. By looking at the numbers, it can show us the population is increasing. To see how much the population is increasing, we have to apply the first order differential equation. We have to derivate and integrate it, and it became P equals to A times exponential to the power of KT, where P is the population and T is time.
Now I will show you guys on how to use the particular solution equation, which is P is equal to A exponential to the power of KT. First, we just have to plug in the initial condition for T and P in the equation to find A, which is the initial amount of quantity at time 0. Now the general solution becomes P is equal to 6,410,000 exponential to the power of KT, and we can also find the value of the constant K by using T is equal to 1 in 2004 and population at 2004. And when we plug in all of the values that we got, we can calculate for K, which is 0.0124. And now the particular solution becomes PT is equal to 6,410,000 exponential to the power of 0.0124 T. Thank you.
Figure 1 shows the actual graph of population in Canada from year 2003 to 2023. From the graph, we observe that the highest population growth in Canada is at year 2023. Figure 2 shows the particular solution graph of population in Canada from 2003 to 2023.
Hi, I'll be sharing with you on how do we calculate the past value of population in Canada. First, we need to let T equals to -1, which is from the year of 2002. After that, by substitute T equals to -1 into general equation that we have calculated before, the answer turned out to be 6,331,006.77. After rounding off, approximately the value will be 6,331,007. By using the data that we obtained, we can calculate the percentage error by simply subtracting the actual data that we get from the graph, which is 6,330,000 minus with the value that we obtained over the calculated value and times them with 100%. And the percentage error turns out to be 0.016%.
I will be sharing on how we predict the future value of people in Canada. So first of all, we set T equals to 1, which is the value that we got from the year 2005. After that, we substitute the T value, which is T equals to 1, to the general equation. After that, we will get the value, which is 6,489,978.844. After that, we round off the value, and the approximate value that we got is 6,489,979. After that, we can calculate the percentage of error from the calculation that we got. So the 6,410,000, which is the value that we got from the graph, minus the theoretical value, which is the 6,489,979, and we need to divide the actual value that we got from the graph, and then we multiply 100%, and the answer for the percentage error that we got is 1.25%.
Now for discussion analysis, we're going to take a very quick look at the accuracy of the calculated values compared to the actual values from 2003 until 2023. As you can see in this table, except for 2003, the other calculated values are closely matched with the actual values each year by year. The differences are very small, which indicates that our formula used is highly accurate over a 20-year period. Next, to measure how accurate our model is, we then take a look at the percentage error for each year by year. And as shown here, our percentage error obtained was very small, often less than 0.5%. The highest error was only around 1.66 on 2023, which is very acceptable for the long-term prediction. Even better, our average percentage error calculated was only around 0.363%.
Why there is difference between the actual values and the calculated value from the particular solution? The differences exist because the calculated population value were assumed to be changed or increased at a constant rate over time. Meanwhile, the actual population values were not constantly increased and can be varied due to unpredictable and inevitable events such as natural disasters, pandemics, and migration.
Now I'll be sharing about what affect the population growth in Canada in the past 20 years. There are two major factors that contributed to Canada's population growth, which are high immigration rates and economic stability. First of all, immigration plays a crucial role because nearly 80% of recent population growth comes from the immigration. Canada attracts many skilled workers, refugees, and international students. Over 400,000 new immigrants are getting each year to meet job market needs. Secondly, economic stability supports population growth through strong job opportunities, high employment, and financial support systems. This helps them to reduce stress, increase birth rates, and improve access to healthcare that will lead to longer life expectancy and lower the death rates.
These are two factors that will affect the population growth in Canada. The first one is declining fertility rate. Many people delay having a children or decided to not have a children at all since they don't feel financially secure to raise a family. This is because raising children in Canada has become extremely expensive. For instance, general living such as food, transportation, utilities, and healthcare continue to skyrocket. The second one is changing values and lifestyle. Many people nowadays tend to prioritize their jobs and education in order to sustain themselves. Most of them agree that having a family is a big commitment and it will limit their freedom and also lifestyle. Therefore, family planning has become more individualistic and based on lifestyle preferences. These are the calculated values that we got from the previous equation that we have made.
To conclude, we have successfully met the objective of task 1 and we are able to use the first order differential equation by using the Malthusian model from the course of MAT097 to calculate the population of people in Canada from the year of 2002 until 2023. We can identify the differences between the estimated population and the actual population using the first order differential equation, and we have calculated the percentage error. We identified the differences and explored the fundamental factors influencing the number of population in Canada. Thank you.
Hi guys, Assalamualaikum. Ani here. So today, I'm going to explain to you guys about task 2. So, let's check it out. Our beloved lecturer, which is Dr. Hashima, has given us these problems that we need to solve it to get the area under the graph. But here's the catch. In this equation, we cannot simply solve it by the normal way, but we can use one of the most wonderful rules in this world, or in this math world, which is the Simpson's rule. In the Simpson's rule, if you use the formula and use the step that has been given in our lecture book, in our textbook, we can get the area under the graph easily. Are you interested in our journey? If you are, then make sure that you tighten your belt and let's go solve this problem with me. Hi guys, this is our Excel as has been completed by me and my teammates. So, with this equation, we can solve it by the Simpson's rule with this formula. So, let's get to it right now. So, we have n, x, fx coefficient and coefficient multiplied by function. For the n is sub-interval, just need to put it 0 until 6. For the x is our boundary to -7 until -1. We need to add the -7 with the h. How to get h? With this equation, b minus a divided by 6. For the function, we can simply add our equation in this Excel and it can help us to calculate it easily. So after that, we can just drag it until -6 and we can give us the correct answer. For the coefficient, you just need to put 1 for the first one, for the first subinterval, which is 0, and 1 for the last subinterval, which is 6. And between that two, we need to put 4 for odd number, 2 for an even number. The last one is coefficient multiplied by function. And after that, we need to total all of it. And from the total, to get the area under the graph, we just need to use this formula, which is H over 3 and multiply by the total itself. So this is our area under the graph for the subinterval 6. For the subinterval 8, it is just the same, but we just need to put 2 more columns, 7 and 8. But the H is different too, because of N is different, which is 8. So we just need to do the same method, and this is our total after calculating. And using the same formula, we can get the area under the graph for N equal to 8, which is 22.03661. And thank you guys, I hope you understand. Bye!
For the graph analysis, let's take a look at both of the graph over here. As you can see, graph 1 is less accurate compared to graph 2. And why is that happening? Both graph 1 and graph 2 show the approximation of the area under the same curve. The difference between them is the number of the subinterval n used in the calculation. As we can see, when we set n is equals to 6, the approximation graph is wider and do not match the curve clearly. This causes the estimation of the area under the curve to be less accurate. Compared to graph 2, when we set n is equals to 8, the approximation shapes become thinner and follow the curve more closely, leading to a more accurate approximation of the area under the same curve. Therefore, it can be said that as the number of the subinterval